All right. So again, thank you all for being flexible about the class, the way we're doing class today. As I said on Monday, this is because I've got a conference, and I would normally be in Chicago for this conference, but with coronavirus, we're doing it all virtual. And so I have a presentation during class time. So because this is going to be completely online and nobody's going to be doing it live, I'm going to go through this a little bit faster, and so we'll be done well before that hour 20 mark. But I would encourage you to pause and think about these, think about the concepts and what we are talking about in such a way that if you have questions, you can jot those down and email them to me or prepare them for class next Monday. So this will be very fast, and I expect all of y'all to pause at different points so you can actually work out the problems, etc., and conceptualize it. But all right, so today we are talking about the t-test for two related samples. I would normally ask, what did we learn last time? So take a minute and think about what we learned last time. Try to think about what were the main concepts. Why did we learn about the independent samples t-test rather than the repeated measures that we're going to be doing today? How is that different from the one sample t-test? How do you go about computing it? What are things similar? What are things different, etc.? But here is your fun fact of the day. The Supreme Court has a basketball court on the top floor of the building, the nickname of which is the highest court in the land. I love that pun. All right. So like I said, today we're talking about repeated measures, sometimes also called dependent measures, t-test. And I think it helps to kind of contrast repeated measures versus independent measures before we get started. So repeated measures have some absolute perks over the independent measures. And one of the biggest perks is that it requires fewer participants than you would need for an independent measures design. And we'll talk a little bit about why that is in just a minute. But when you're designing experiments, if you have the opportunity to do a repeated measures, you want to, because it requires less time, effort, and energy on your part to get more participants, etc. In addition, the repeated measures design is particularly well suited for examining changes that are occurring over time, such as learning or development, etc. And so one of the examples we're going to be talking about today is pre and post, right? And so you can see, okay, what sort of effect does a certain educational intervention have on student performance, right? So you have pre, you have post. You can look at learning over time. How good do people get as they progress in age? You could also do things like wanting to see what sort of effect old age has on cognitive abilities, right? So you could sample some people at age 50 and then wait to sample them again 25 years later and see at 75 what sort of diminishments do they have in their actual abilities. So the primary advantage of a repeated measures design is that it's going to remove variance and error by removing individual differences, right? And so what we talked about with our independent measures t-test was that you had one group that served as kind of the control, right, representing the population. Here, you're going to have the group that is the treatment condition also serving as its own control, right? Because whereas with the independent measures, we had one group that was just doing the driving test and another group that was doing the driving and texting intervention, you're going to have some individual differences, right? And so we talked about one of the things, we want to make sure we weren't just sampling the really bad drivers and putting them into that texting condition. So when we're doing this repeated measures, we'll have people drive by themselves, and then that same group of people will drive with texting. And so now every person serves as their own baseline. If they're a really bad driver, that's going to come out in the just normal driving task. And that way, when we see really bad performance in the texting, we know if it's really bad performance because they're just a bad driver, or if it's because of this intervention, right? Maybe they were an okay driver without texting, but once you add the texting, they become awful. And so, whereas with independent measures, we had two different samples and we were calculating the difference between those two samples, for the repeated measures T statistic, you're going to be finding the difference score for each subject, right? So how much different is their score after that intervention? So how much different is their score in the driving and texting condition than it was in just the driving? And you find that for each subject. And we'll go into a little bit more detail in just a few minutes. Ooh, I just splashed coffee on my face. Excuse me. Yeah, so the perk of doing this type of test, like I said, is that you are having every participant serve as their own control, right? So the D score, so that's just gonna be the difference score, for each subject is gonna provide an indication as to how much difference there is between the two conditions, between the control and the treatment condition, or two different treatment conditions. If all subjects show roughly that same D score, you can conclude that there appears to be consistent, systematic difference between the two treatments. You should also note that when the D scores are similar, the variance of the D scores will be small, right? Which means that the standard error will be small and the T statistic is more likely to be significant. So where you've got consistency in that difference score, in that D score, you're going to have reduced variance, which is going to make it more likely that you're able to find a significant effect because you've reduced any potential assumption of kind of sampling error in there because of that consistency. You should also note that the process of subtracting to obtain the D score removes the individual differences from the data, right? And so we already talked about this just a few minutes ago, but by having every individual serve as their own control, we now know that if you're a bad driver when you're texting, but you're an okay driver without texting, the fact that you're a bad driver while texting is likely not a function of us just having sampled you as a bad driver in general, but is a function of your inability to drive while you're texting. So the initial differences in performance from one subject to another are eliminated, right? So you don't have to worry about that source of variance. Removing those individual differences also tends to reduce the variance, which creates smaller standard error and increases the likelihood of a significant T statistic. And so let's just look at this with actual numbers, right? And so let's say we have 5 different subjects. If we were to do an independent samples t-test, right? If this was sample 1 and this was sample 2, you can see that there is a lot of individual difference in these scores, right? Ranging from 9 to 72 or 16 to 79, right? This is a massive source of error, just as a function of, okay, if there's this much variability in subjects, we don't know if this second sample has a mean higher than this first sample, if that mean difference is just because of sampling error, right? If there's that much variability in the population, we're going to have to find a massive difference to be able to say, okay, this is probably not due to sampling error. This is probably due to an actual treatment effect. However, by doing an individual differences, or excuse me, by doing a repeated measures test, we remove those individual differences such that we get this difference score, this D score, right? So it doesn't matter where they are on that absolute scale. What matters is their difference from point A to point B, or time 1 to time 2. Right? You can see how this significantly reduces the variance that you find here, right? And so that's going to make it a lot easier to have confidence that any actual mean difference that we would get here is likely due to a function of this treatment having an effect, right? Adding that texting likely made them worse drivers. So again, from that data set, notice that all the subjects show an increase of about an average of 5 points, actually an exact average of 5 points, when they go from treatment 1 to treatment 2, or pre to post. Because that treatment is very consistent, those D-scores are all clustered close together, thus producing a really small variance, subsequent standard deviation, and then standard error. Right? Because the standard error is going to be the denominator of that t statistic, as it was with the one sample and the independent measures. This means that the t statistic is likely going to be higher because we've reduced that standard error in the denominator, right? We can keep that mean difference the same in the numerator, but by decreasing that size of the standard error in the denominator, we're now able to say with greater certainty that the difference in the numerator is likely representative of a real effect because of the small variability we have in those different scores. Right? And so this makes it easier to study small effects, right? So we talk about effect sizes. Having these small effects, you can have a much smaller sample and still find a significant effect because you're not worried about potentially large variability in what's in just the sampling error, right? The individual differences, things like that. So again, notice that those original data are showing big differences from one subject to another. Right, so subject B has scores in 20s, subject E has scores in their 70s. Like we've already said, those big individual differences, the differences between people, are eliminated when the different scores are calculated, right? So we've just completely neglected one major source of error or variance. Because these individual differences are removed, the D-scores are usually much less variable than the original scores. And again, a smaller variance will produce a smaller standard error, which will increase the likelihood of a significant t statistic. The smaller the denominator, even if you keep that numerator constant, the bigger that t statistic will be. However, there are disadvantages to doing a repeated measures design instead of an independent samples, right? And so I would think, pause this and just think about what are some of the potential consequences, without reading the slide, for doing a repeated measures. All right, so hopefully you did think about that. One of the consequences of doing a repeated measures design is that sometimes you can't actually have participants complete both conditions, right? If I'm testing the effectiveness of a COVID vaccine, I can't necessarily have people in two different vaccine conditions, right? Because if one vaccine works, then I can't tell about the other vaccine, right? It's also possible that by having people in both conditions, they're able to intuit what the purpose of that study is and try to adjust their scores accordingly, right? If I know that somebody is testing a memory drug, right, to help my performance in school, and the first treatment I get is just the control, I have to take a memory test, and then I get that memory drug. If I then decide, okay, well, they're obviously testing the effectiveness of this memory drug, maybe I just try harder, right? Because I want to play into whatever the purpose of that research is. So I'm trying harder, I actually do better, my memory scores increase. Or you sometimes get people who say, you know what, screw this. I know what their purpose is, and I'm going to screw with their data, right? Unfortunately, that does happen. And so when you have that type of setup, excuse me, you'll sometimes get kind of negative effects of people deliberately manipulating their data based off of what they think the purpose of the experiment is, right? So it's not always the case that repeated measures designs are always going to be better than independent measures designs. You can also have a case where practice in that first treatment causes improved performance in that second treatment, right? If I want to see how good you do, I want to see if caffeine helps you on a test, a math test. If I give you a control test for math, have you take that, and then give you caffeine and have you take the test again, or even a new test, the mere fact that you were practicing, you know, kind of jogging your memory about math concepts, about order of operations, etc., could have affected your score on the second test, irrespective of any potential benefit of caffeine. And so scores in the second treatment may show a difference, but that difference may be by maybe a function of just practice effects, right? Not necessarily that treatment or intervention effect. So when participation in one treatment influences the scores in another treatment, the results may be distorted by what we call order effects, right? And so again, the order of the conditions, that practice, and then with the caffeine for the test, can be a real source of issue for these repeated measures designs. And that's one of the reasons why we advocate for counterbalancing, right? And so maybe it makes sense to have people come in on one day, take the math test, and then another day come in, take another math test with caffeine, but perhaps you want to avoid any potential order effects. So half the group will do that initial flow of practice and then the next day with caffeine, whereas the second part of the group will do caffeine test first and then just the no caffeine test the next day, right? And so that way we can say, okay, if there is a similar benefit, regardless of which direction, which order, which presentation you get, we can say that's probably due to the caffeine. Otherwise, we're going to have a hard time saying this is due to caffeine and not just due to practice. All right, so this is just regurgitating everything we've already said. So in the repeated measures design, we're using a single group of participants, right? One group of participants, and we're getting two scores from them. Either two treatment conditions, a pre and a post, a control, and a treatment condition, etc. So data is going to consist of two scores for every individual, but we're going to find that difference score, the difference between their two scores. Right, and so that difference score, represented by D, is just going to be x2 minus x1, right? The second score they have minus that first score. So in this case, it would be the driving while texting minus just the driving. This related samples t-test can also be used for what's known as a matched subjects design. And a matched subjects design is where we get two different groups, but we try to select participants for each group that are as close to a perfect match for the other one, right? And so selecting a pair of subjects so that two subjects in each pair have identical or nearly identical scores for that variable is being used for matching, right? So you get the benefits of trying to eliminate the individual differences, but now you don't have to worry about some of the order effects that we just talked about with those repeated measures. But regardless, the principle is going to be the exact same, right? You're going to be finding that difference score, that D score, for each of those pairs. Again, this is just reiterating what I just said. You're going to find that difference score for each of those matched pairs, right? So you're going to either be finding the difference score for one participant, time 2 minus time 1, or you're going to be finding the difference score for those matched participants, right? So you want to, again, get people that are as close to each other's scores as possible at the start during that selection, so I can reduce any of those individual differences effects, and I get a D-score that will likely be representative of the actual difference associated with the treatment. And so the sample of difference scores is used to test the hypotheses, about the population of difference scores. All right, and so whereas we were using the actual scores themselves for the one sample t-test and for the independent samples t-test, for the repeated measures t-test, we're using the difference scores for every calculation we're going to be doing, right? And so the null hypothesis for these repeated measures t-tests, when you're doing a two-tailed t-test, is that the population of difference scores has a mean of 0. Right? So I'm taking all the different scores and I'm averaging them together. The null hypothesis would be that those equal 0, or not statistically significant from significantly different from 0. So again, we have a population of different scores with an unknown mean. We sample 4 participants. We get their scores at time 1, we get their scores at time 2, and now we just calculate that difference score, right? So it's going to be time 2 minus time 1, so you get 4 for subject A, -2 for subject B, 3 for C, 1 for D. Okay? And so these difference scores are what we're going to be doing all of our calculations on, right? And so anytime you've got a repeated measures test, you first need to get that D for every individual subject. So again, the null hypothesis says that there is no consistent or systematic difference between the two treatment conditions, or the pre and post, or the treatment and control. Note that the null hypothesis does not say, excuse me, that each individual will have a different score equal to 0. So it's not saying that every D score will be 0. It's saying that the average of those D scores will be 0, or at least close to 0. So on average, that entire population will show a mean difference of 0. Thus, according to the null hypothesis, the sample mean difference should be near to 0, or any small variance would just be due to sampling error. The alternative hypothesis, or the research hypothesis, states that there is a systematic difference between the treatments that's going to cause the difference scores to be consistently positive or negative, and produces a non-zero mean difference between the treatments. Right? So this alternative hypothesis, or this research hypothesis, is saying that the mean of difference scores is not equal to 0. It could be higher than 0, it could be lower than 0 if we're doing a two-tailed test. If we are doing a one-tailed test, a directional test, this will be designated accordingly, right? And so if we're expecting that their post-treatment scores are going to be higher than their pre-treatment scores, you would have a mu subscript D, right? So that mean of differences is going to be greater than 0, right? So the null would then be less than or equal to 0. And so this repeated measures T statistic is going to form a ratio with exactly the same structure as that single sample T statistic, right? The numerator of the T statistic measures the difference between the sample mean and the hypothesized population mean. Right? And so this is going to be an important distinction. You're going to see in just a minute that the numerator is going to be the mean of differences score minus the population, the hypothesized population difference score, right? And so in almost every case, this is going to be 0. Again, I'll show this to you in just a second. But in almost every case, this is going to be 0, such that you would only plug in a number into the hypothesized population mean if you had some knowledge of like the order effect, right? And so if I know, if I give you test 1 and then test 2, that you're going to perform 3 points better on test 2, regardless of whether I give you caffeine or not, I will subtract that 3 because that's just an order effect, right? That's noise that I want to just get out of there, right? And so if the mean difference between time 1 and time 2 is 5, I would be subtracting that 3 because 2 would be the actual real kind of treatment effect size. So again, the bottom of the ratio, just like with the single sample t-test, is going to be the standard error, right? It's going to be represented a little bit different than we've done so far, but it's going to be the same conceptual way of calculating the standard error as with the single sample t-test. So again, your t ratio is going to be your obtained difference minus, your obtained difference divided by the standard error. So up here, we have that mean difference, right? The mean of those different scores. You calculate the D, you calculate the mean of those Ds, and subtract any of that hypothesized population difference score, right? So this would be that 3 in the case where I said we know that there is an order effect or a practice effect that we want to get rid of. Normally this is going to be 0, so it's going to be the mean of those different scores divided by the standard error. Degrees of freedom, as with before, is just going to be n minus 1, right? And so because you only have one sample, it's not going to be the number of measurements, it's just going to be the number of subjects, right? And so if you have 10 subjects and you have an A and a B condition, your degrees of freedom is not 20 minus 1, it's 10 minus 1, right? So it's just the number of subjects minus 1, not the number of observations minus 1. So as I said before, for this repeated measures t statistic, all calculations are done with the sample of different scores. You're taking your x values, you are finding the difference to get that D score, that difference score, and then you're essentially disregarding the x values from there on out. Everything you do, calculating the sum of squares, calculating variance, standard deviation, standard error, etc., is all based off of those different scores, those D scores. And so when you calculate the standard error, it's represented different than the standard error for the single sample t-test, even though the equation looks the same, because importantly, this is the standard deviation of those different scores, right? This is not the standard deviation of any individual X score or any of the treatment conditions. This is the standard deviation for those different scores that you've calculated. And we'll go over some examples in just a second. And this is still over the square root of n, so the number of samples that you have. Or excuse me, nope, not the number of samples. The number of participants you have, not the number of observations, not the number of samples. So if you have 10 participants, 2 treatment conditions, pre and a post, again, that n would be 10, that n would not be 20. So the equation for sum of squares is going to be the exact same, except instead of x, we are now substituting that D score, right? Because everything we're doing is with the difference score rather than the individual x, right? So it's still the sum of D squared minus the sum of D, close paren, squared over n. That variance is still the same, sum of squares divided by the degrees of freedom. So you can see it's the exact same thing, but the reason we add this different signifier is because it's not X, right? X indicates an individual observed value. The D represents the difference score between two values. So here's an example. Question, do college guys tend to date college gals that have higher IQs than the guys, have? 10 college couples are randomly selected and each member is given an IQ test. Perform a one-tail t-test at the alpha of 0.05. And so here are the 10 samples, right? So this would be, 110 IQ for the guy, 105 for the girl, 100 for the guy, 108 for the girl, etc. Right? And so let's actually go ahead and calculate this. Let me make sure. Let's just go here first, and then we'll actually calculate. All right, so the first thing is to establish what is the null hypothesis. Right? So the null hypothesis is that the mean of difference scores is going to be less than or equal to 0. Right? So the hypothesized value is that, or the null hypothesized value is that these difference scores indicate that the girlfriends are as smart or less smart than the guys. The research hypothesis is that mean difference is going to be greater than 0, or such that the girls in the relationship will be significantly smarter than the guys in that relationship. And so we're testing at the 0.05 level. Again, that's our alpha of 0.05. And we're going to go look up that statistic in the back of our book, right? And so if we go to the degrees of freedom, we know we have 10 subjects. So it's going to be 9 degrees of freedom. And we're going to be looking up 0.05 in one tail. And that gives us 1.833. And so we're just going to simplify that to 1.83. All right. So first things first, let's go to our data here. And so we have the boys' IQ score and the girls' IQ score, right? So first things first, we have to calculate the difference score. So we're going to, for each subject, take the second, or in this case, the girls' IQ score, and subtract their boyfriend's score. Right? And so we'll do that for all of them. And so you can see this is the difference score, right? So for this couple, the girl had an IQ of 5 points less than the boy. Here, the girl is 8 points higher, 10 points lower, 5 points higher, 3 points lower, 10 points higher, etc. Right? And so now, everything we do is going to be with these scores here. We're just going to ignore these scores from here on out, right? And so let's first find, well, we're going to have to find several things, right? We're going to have to find the mean. We're going to have to find the sum of squares. We're going to have to find the variance. Where is my superscript? I can't find it. All right, so we'll just, this will just be s squared. This will be s. And then we're going to have to find our standard error. Cool. All right, so for the mean, we're going to find the average of all of those different scores, gives us 0.6. Right, so this is saying that on average, it seems to be that the girls are a little over 1/2 of an IQ point smarter than their boyfriends. So now let's find the sum of squares. I'm just going to do this in Excel, but again, the equation for that is the sum of d squared minus, in parentheses, the sum of d. You're going to then square that sum of d over n, and when you do that, you should get 516.4. Let's go ahead and find the variance. Again, because this is a, because this is a sample, you're going to be dividing by n minus 1 and not just n. And when you do, you should get a variance of 57.8 377, right? So it's just this divided by 9. For the standard deviation, again, this is going to be for our sample. We're then calculating on standard deviation. The standard deviation should be 7.57. And then for our standard error is just that calculated standard deviation of the difference scores divided by the square root of n. And we have 10 subjects here, or 10 pairs. And so this is going to be equal to that standard deviation that we just calculated divided by the square root of 10. We get 2.395, or we'll say 2.4. All right, and so now we need to calculate that t-score, right? And the t-score is just going to be that mean difference minus the hypothesized population difference. And in this case, we don't have any reason to believe that there is something in the population that should make us subtract values. So it's just going to be 0.6. So we'll do this equals 0.6 minus that 0, because we, again, don't have anything in the population that makes us think we should subtract something from this. And now we're going to divide it by our standard error that we calculated down here. So 2.4. And that gives us a t-value of 0.25. All right, so let's go ahead and look this up. Let's see, our mean 0.6, our sum of squares 516.4, variance 57.38, standard deviation 7.57, observations 10. Yet again, this null mean difference is 0, degrees of freedom 9, standard error 2.4 like we calculated. The t statistic that we calculated was 0.25, and our critical value was 1.83. And because we were less than that critical value of 1.83, we retained the null hypothesis. So we would say there's no significant difference between college couples on their respective intelligence. All right, let's work another example. So, does Dr. T's miracle memory legume make you smarter? Right? We did this for the practice problem for a one sample t-test, I think it was. Below are the test scores pre and post legume consumption. For those of you who don't know, a legume is just a bean. It's like a magic bean. So test at the 0.05 level in one tail. All right. So we again need to find our critical t value. So we have 5 pairs, right? So our degrees of freedom will be 4. We're going to test at the 0.05 level in one tail. So I'm going down to 4. I'm going to 0.05 in one tail, going down, and when I do, I get 2.132. All right. I need to change this real quick just because I think I screwed that up earlier. All right, ignore that. All right, so let's go to our data once again. Ignore all this. It was just me making sure my calculations are right. So we have our pre-legume consumption and our post-legume consumption scores. Again, we need to find what is the difference score here. Because we're hypothesizing that the second one is going to be bigger than the first one, it makes sense to have that second one minus that first one, such that any positive score indicates that it is in fact better, like there was in fact a benefit of taking that legume, whereas any negative score indicates that it hurt performance, right? And so we're going to calculate that difference score for each one of these, and you can see that for subject 1, there was a 4-point increase, subject 2, a 1 point, subject 3, no points, for subject 4, a 7-point increase, and then for subject 5, a 2-point increase, right? And so what do we need? We need the mean, we need the sum of squares, we need the variance, we need the standard deviation, and then we need that standard error, right? And so, again, everything we're calculating is based off of these difference scores. So let's go ahead and calculate that mean. Whoops. So we're taking the average of those 5 scores, we get 2.8. So on average, across these 5 participants, there was a 2.8 point jump from the pre to the post. But we need to see if that's significant. So we need to get our sum of squares. So again, that's going to be the sum of d squared minus the sum of d, square that, divided by n. When we do that, we get 30.8. The variance is going to be the variance of the sample again. So divided by n minus 1. So it should be this divided by 4. And you can just do a quick sanity check on this. So divided by 4 gives us 7.7. Perfect. All right, and for our standard deviation, we have to find the standard deviation of our sample here. Gives us 2.774. All right, so now we have to find our standard error. So again, remember our standard error is the standard deviation of the mean differences that we calculated divided by the square root of n, so the square root of 5 in this case. So if we do that, we're going to do that standard deviation we just calculated divided by the square root of 5. And we get 1.24 for our standard error. So now our t statistic is going to be that mean. So we're going to do 2.8 minus, we don't have any hypothesized population difference, right? There's no reason we should be subtracting anything other than 0 in this case. So we're going to subtract 0. And now we're going to divide it by the standard error we calculated down here of that 1.24, 1.24. And that gives us 2.258 or 2.26. And so when we go here, let me just round this up. And because I was wrong on that, we're going to reject the null hypothesis, right? Because this is more extreme than that critical one-tail value, we're going to reject the null hypothesis and say that my miracle memory legume does help with test score performance. All right. So you can also compute an estimate of Cohen's d to obtain that standardized measure of mean difference, or you can compute that r squared again to obtain a measure of the percent of variance accounted for by the treatment effect as we did before, right? So Cohen's d is just the average difference over that standard deviation, right? And so in this last example, that average difference is 2.8. The standard deviation that we calculated is 2.77. And so we would do 2.8 divided by 1.77. And if we do that, equals 2.8 divided by 2.77. Whoops, screwed up. 2.8 gives us a Cohen's d of 1.01. So that's a big effect size, right? That's saying that you have a 1 standard deviation increase in your performance as a function of taking this miracle memory legume. Again, to compute that percentage of variance explained, r squared is just going to be t squared divided by t squared plus the degrees of freedom, right? And so if we're getting this r squared value here, it's going to be our t squareds, we're just t times t. And so now we're going to do this divided by that t squared plus the degrees of freedom. So degrees of freedom in this case would be 4. And our r squared is 0.56, right? So this is saying 56% of the variance in this difference score can be explained by the consumption of that miracle memory legume. So hopefully that all helps. Again, I know we went through everything fast, but with it not being live, I figured it makes sense for you to just pause the video where appropriate, or where you needed to pause the video. If you do have any questions, please feel free to email them to me, or we can go over them at the start of class on Monday. I hope you all have a wonderful weekend, and I will see you next week.